Hello, everyone. Welcome to Exploration of C++ Metaprogramming 20, of course. And I'm really glad you joined me today. So today we're going to talk about C++ 20 metaprogramming. But first of all, I'm going to introduce myself. So my name is Inbal Levi. I'm a C++ enthusiast, and I'm an embedded software engineer, and I work at SolarEdge on smart home devices. I'm also one of the organizers of CoreCpp conference, and this is an user group, and this is the largest user group for CPP in Israel, along with Adi Shavit and Michael Goldstein. And I'm also a member of Workgroup 21 and one of the founders of the Israeli national body of the C++ ISO conference. I've studied physics, and I also love math. So if anyone wants to talk about math later, I would love to. So let's start with motivation to this talk. So templates are a powerful tool for C++ programmers, and I'm sure that everyone here is aware of that. Each C++ version have evolved and evolved this topic, and by each C++ version, we can see better usage in this mechanism. We'll see the value of adding templates in your code. And I just want to add here that we're going to start as if no templates are part of our code base. And this talk is for intermediate and beginners, but I also think it has some very interesting general C++ 20 guidelines for advanced programmers. So some environments discourage extensive use of templates, and I'm not sure if you guys are familiar with this style guide. If it were in a real world, I would have asked you now to suggest where is this style guide, which company this style guide belongs to. But this is the style guide of Google, which is a very advanced company, I would presume, and they're suggesting to avoid complicated metaprogramming in the code base. And I actually don't blame them. They have a really good reason, because templates considered as an advanced topic and for experienced engineers, and you want to have your code base available to different levels of developers, especially if you recruit new ones, etc. So I would hope that on C++ 20 we'll have syntax that allows more developers to use template metaprogramming. And in the following slides, we see how C++ 20 actually, to my opinion, creates a paradigm shift in the way we use metaprogramming. So this is the outline of our talk. So first, we're going to start by introducing what are templates. Then I'm going to continue, as I said before, by adding templates to existing code. I'm going to go over overload resolution and ADL, which are important topics in order to understand template metaprogramming, but they're also important in general. And then we're going to move to conditions at compile time before C++ 20 and conditions at compile time using C++ 20 and beyond. Some of the things that I'm going to show at the end are not part of the version yet. I would hope in the future there will be. And at last, we're going to look at the advanced method for controlling compile time logic. So let's start. What are templates? So as I said before, we're going to go over this very briefly. So templates can be used to create a class or a function. And here we can see the template for having a class type. And you can see that you're accepting type here. And you can use the type in your class. You can also not use it if you prefer to. But this type is available to you in the definition. And this is how you will define a template function. So you accept, again, the type here, and you use it. And there's additional way to do it. And by taking the type that you've passed, you can actually take it as a parameter for the function. But you don't have to. And I'll show later the two different versions. And again, I would say that this talk is not introductory to template metaprogramming, but it assumes that you do familiar with it. But again, you're not a library author, basically. But there are two very interesting talks in this conference, and I mean, actually two talks that are double talks. And one is Back to Basics for template metaprogramming, and the other one is for type traits. I will mention them later. So, function template is usable only if you can see the definition. So clearly, declaration is not enough, just like in regular template function. And there's two ways to have, so this is the declaration, this is the definition. And there's two ways to have explicit instantiation for template function. And there's a few ways to have an implicit instantiation. Now, this is useful if you want to implement a library, a template library. Then there's two ways you can do that. The first one would be to expose your definition in the header file, of course, the declaration as well. And in that case, the user would be able to instantiate your templates, your library, for every type that he desires. And the second way would be just to have the declaration in the header file and the definition hidden. And then in the header file, you could use this methods, basically this syntax, to explicitly instantiate your templates and therefore limit the types that the user can use. And this would be like a closed interface. And another thing I would like to point out is C++20 adds a syntactic sugar for this function template declaration. I actually chose not to use that for the talk because I still want this to be somewhat introductory level, and it uses auto, and I would think that it might be a bit less explicit. But you can search later, and there's a way to do that. It's called arbitrary function template declaration. So, as I said, templates are evaluated at compile time, and they're also Turing complete. That means that you can achieve any functionality of Turing machine with templates, and they have few layers of usage. So I've mentioned that before. I'm just summarizing here that first of all, you can use them to avoid rewriting repeated logic. So clearly, when you write something once, it's less error prone, and that's a good practice in general. And they can also be used to write generic code. As I mentioned before, you can use them in order to provide a library in two ways that I mentioned. And they provide a mechanism for moving logic to compile time, which is actually, I think it's the most interesting thing about templates. So in the simplest ways to use generic extra code is they have, I mean, okay, sorry. You would expect that by having the template as a generic extra code, way to perform extra code, it will create some overhead in instantiation. But in fact, they actually have similar size, and their and the compilation time is also similar to regular code. So this is very useful if you are not sure which types you're going to have in your program. Okay, adding templates to existing code. So first of all, consider this following template-free code. So I will just go briefly on the overload resolution. So overload resolution is, of course, by parameter, and you can see here there's an int and a float and some class C. And you could call the functions, call the overloads by calling the functions, and you have all the different types that you we have instantiated before by declaration. Of course, if you add another declaration, that will be ambiguous. And the issue here is that if you don't use this version for some class in your code, but you're not sure, you want to be able to add it later to the code and say this is the library, then you have to instantiate the declaration, of course. So we could replace the overloads by a single template function. And in this way, we have two main advantages. As I said, we're saving coding time and code duplications and less error prone. And in binary size, as I said before, we don't have to explicitly instantiate all the different types the function is getting. We could, in case we're providing a generic library, we could just have this instantiated by the user's will. So partial specialization is also available. So first one is partial specialization of a class. And in this case, we can have a full type class that calls full type that takes two types for two template parameters types. And the second one that can actually take the same type. And of course, if we'll call the full type with same type, we'll get the call to the specialized version that we requested. By the way, all the snippets of codes will be available later, and I'll post them in my GitHub as Godbelt links. So you're most welcome to play with the code. So partial specialization of a function is a bit different. And by the way, it's not always called, not explicitly called like that. But you could see here in the example, there's a wrapper. And this is a function that takes a type, foo that takes a type, and the other function takes a wrapper. And when you call the foo, you get the appropriate call. Actually, that should be a large case, according to what we were expecting. But I'm not getting into this in details here, but pay attention that there might be namespaces issues here, and you will need to consider if your type is exposed, if the template is available in the scope. All right. Overload resolution. This is our next topic, and this relates to what I just said, but I'm not going to elaborate on that too much. But I will mention the main few guidelines that we need to remember when we are instantiating templates. So first of all, the compiler creates a set of candidates, and all functions that can have that can be suitable for our call. And then the compiler creates a subset of viable functions that's actually suitable by name and parameters. Also by partial ordering of function template. That means that the most specialized template is instantiated, and template argument deduction. I will elaborate a bit more on those on the next slide, but in general, the best viable function is the one that whole parameters have either better or equally ranked implicit conversions. So if we have two of those, then we'll be ambiguous. And member functions gets their class parameter as a first parameter, of course. So as I said, name lookup. All the functions with suitable names are associated with the function call. And partial ordering says that we choose the function template that is according to the specialized version, as we saw before. And ADL actually means that in addition to the namespace that the function is located at, the compiler will look for suitable functions according to the parameters being transported to the function. So again, as I said, ambiguity can be created if we have more than one viable function. And we will get an error if no candidate function is found in case we called it. But if we haven't called it, then notice Sphene is something that is widely mentioned. And again, I'm not going to go too deep to that direction in this talk, but if we're not, the error would be as part of the calling for the function and not part of the unfound match. So let's go over conditions at compile time before CppCon. So first of all, conditions and compile time have a very powerful tool that they're using, and that's called type trait. Now, type trait are a library, and they're clearly verified at compile time. And a type trait contains a member which is a Boolean that can be either true or false. You can access that member either by value, by addressing directly to the value. Since C++17, you can also access it by using the trait name and then _v. Some new type traits have been added to C++20, and we're going to go over them a bit later. But in general, a function type trait is also something that is new for C++20, and function type traits would be a context pair function, and generally they identify a situation. So a general overview on which type traits do we have? Just briefly, again, I'm not going to go too deep into that. If you're interested, the talk by Jody Hines in this conference is going deeper into the different type traits and implementation and demonstrate implementation. But basically, we have things like helper classes. We have a way to identify the type of the type, the reference versus pointer, type properties, relationships. In addition, you could also have remove references and pointers, and signs, of course, change the signs, and an additional very interesting thing, I think, is the operations on traits, conjunction, disjunction, and negation. They were all added in C++17, and we will address them very briefly because they're also very relevant to C++20, I believe. So in addition, as I said, we have the functions type trait that were added in C++20, which is corresponding member, is pointer invocable with class, and is constant evaluated. That, I believe, is the most interesting one. So two main types of conditions exist. So the first one would be, and this is just my sort of identification, it's nothing official. I mean, I haven't found some official declaration for that, but in a way, you could define your type as define Boolean that defines your condition and then evaluate it. And a different way would be to create a function that can evaluate the type and do something accordingly. So these are like two main, I would say, main ways to address the condition. And notice that you can, here I haven't even used the types in the function. So basically this is created in order to identify a situation. So there's two ways. The pre-C++20, there were two ways to define functions conditions. The first one would be with enable if. So you can see here a function print triviality, and for trivial types, the overload will be the one on the top. for non-trivial types, we'll get here. Now we have this, as I said, enable if functionality that by default it returns void, and the idea is that if the condition is not met, this function will not be defined, because this actually defines the return value of the function. And here we have, as I said, similar overload by non-trivial types. So we basically covered the cases here. And a different way to define this condition is available from C++17, const if, which is stated here. And you could basically check the condition. As I said, type traits are compile time. So you could check the condition and then evaluate your path for the function. Notice here that this print triviality function is always created, unlike here. But it effectively does the same thing eventually in the code as well. Sorry, this was not in use. All right. So as I said before, we're going to focus on conjunction, disjunction, and negation because they're going to be broadly used once you move to C++20, at least I would expect. And conjunction is clearly an OR operator, and AND operator, and you could have the, as I mentioned before, you could have the form of is all same that doesn't take parameters, and the form of is all same that does take parameters. Here specifically, it's taking a parameter pack, and again. There's two main talks in this conference, and you could look at Back to Basic track for templates to understand better parameter packs. And again, as I said, this is the forms, and you can use this as a Boolean to evaluate the state. So disjunction is very similar, and here you can see this function that evaluates the condition, and again, it can do something with it either or just return it, and that would make it closer to concept in a formation. And negation is again part of the stud negation, part of the type traits. Now, the reason I'm using those versions, and I think that you should too, is that those versions over and, or, and negation that are marked in signs, these forms will optimize and in case when they open the parameter pack and will not instantiate if the condition is met. So this is actually sort of a lazy evaluation, more effective. So, okay, so this was the sort of the boilerplate of the talk, and now we're reaching to conditions at compile time using C++20. So, as I mentioned, C++20 created a paradigm shift, and concepts and constraints are, I think, a very powerful tool, and I think they're also changing the way we look at the language. So, again, as I mentioned, I come from I'm very fond of math, and I think that in a way they give us a broader definition in which we can use for type category versus type as we did before. And it is true that most things that you're doing with C++20 were accessible before concepts, or at least I would think most usable, most common use cases, but still it's a much powerful tool, and I think it's worth exploring. So as I said before, basically before C++20, I would think of that as having a condition and defining a type. And you can look at the type and understand if the type is evaluated, if the condition is evaluated to true. And I think in a way, concepts allow you to define something that is broader and as a type category. So In the following slides, we will review, as I mentioned earlier, C++20 new type traits, some new syntax for controlling the overload sets, and new tools to use when you're using C++20 and a bit beyond. Some of the tools are actually not part of the language yet. So as I mentioned before, type traits were added for in C++20, and I think they're very interesting. There are very interesting type traits here. I've mentioned before the functions, some that defines member relationships, is pointer invocable with class, and is corresponding member, and is constant evaluate, of course. And if you look at those type traits, I wouldn't go too deep into each of them, but if you look at them, you can see that they have something in common. And the thing in common is that they provide better reflection abilities. So basically, I think that they expand broadly our ability to use the language. And I think along with concepts and constraints, the new type traits are also very valuable tools. So, okay, concepts. So concepts are a way to define restrictions. As I said, I would refer to them as defining type category. The expressions in the concept are only validated, they're not evaluated. So a condition can be either a simple condition, true or false. It could be a requires expression, which will return true if valid or false otherwise. And it could be a requires expression that describe requirement under return value as well. So you can define with this syntax some condition under return value. Here you can just here you're just defining conditions on the accepted type. Again, as I said, their concepts are used to identify if a type belongs to a certain type category. So I would say that concepts, in a way, I think they're easier to read. You can judge by for yourself, but I think that concepts are easier, more expressive way to define what we want in our program. So here I define this trivial concept type, and just a few short limitations. Concept cannot contain, cannot be constrained. That means that you can't accept, you can constrain a concept with a different concept, and they cannot recursively refer to themselves. And these are things that needs to be considered when you define concepts and where you heavily use concepts in your code base, which I would hope you will. Just another short boilerplate. A popular way to declare a concept could be, I mean, again, in this talk, I'm mentioning the return types, etc. And of course, I'm avoiding things like reference semantics and so on, but I'm defining the return types, and you could basically avoid that by using concept pair auto. Of course, it's less, I think it's less understood in a presentation. So concept, okay, so again, these are the concepts that were added, and they're all, of course, added in C++20. And I'm not going to go over each of them, but you can, I think you can recognize that they are very strongly coupled with the type traits, and it's, in a way, they're basically a clear way to define the very similar conditions as in the type traits. And you can see here that there are comparison concepts, object concepts. Some concepts are part of the core language, and callable concepts can evaluate the, I would say the evaluate the callability of the type. So constraints are what you're doing when you're using a concept in order to restrict your overload resolution.
So in this example, we have the requires concept that we defined before, and the integral concept that we defined before, and we require this integral to be to restrict the full function. And constraint can also be defined in the form of to me at least resembles enable if. So this is very similar to what we saw before. Before we saw enable if here that defines whether the function is going to exist or not. And I would think that this is very similar syntax. And eventually, I just want to mention that, as I said before, the Sphina issue that will be here would suggest that, I mean, if I wouldn't have called this function explicitly, I would, I mean, the error comes from the fact that I'm trying to use the function and not by just the fact that I couldn't find the overload resolution. Okay. So constraints, as I mentioned before, are expressing additional data on the type, some restriction, and constraints can be used to restrict either time-place parameters or variables. Their normalizing process of constraints is as follows. Basically, unpacking the constraint and having a conjunction between the different constraints. And they can be added to the code in the following 4 ways, and by the order. So it could be in the declaration of the template parameter, using requires clause after the template parameter list, using as a placeholder type to arbitrary function template declaration, as we mentioned before, and trailing requires clause, as we mentioned. So I'll just introduce those 4 ways. Again, as I said, in the following order, and this is interesting because I refer to that later. So in the declaration of a template parameter, you can see here the integral concept. Using require clause after the template parameter list. So this is the enable if form. Using concept as a placeholder type. This is actually relevant when you use the advanced form, as I mentioned before, for defining template function. And this is the way to do it for parameter pack. And using require clause after the template parameter list. So this is, again, this is the order which the conditions are evaluated. And this is, I think this is important we'll see later why. So let's go to real world use case, a wrapper type. So the type category, again, can be used, to my opinion, in a broader way than the classic template metaprogramming style. So we start with defining a concept that's called contains data, sorry. And this concept contains data requires that the type that we get here will have we passed here will have a data member. So that type that satisfies the concept that I described above would be something as follows. And you can see here the data type. Now we can define this wrapper class that can only accept types that have the data member. And here you can see we're using our concept defined before. And this is, again, it's not necessarily to use the whatever constraint that you've added to the function, but in this specific example, we're actually using the data that we defined is required here, and as I mentioned before, we can either succeed when we instantiate, when we actually try to call the function type, or we can fail, and in this case, we'll get an error because the function was not found. Sorry again. Again, I haven't mentioned that before, but I'll probably take questions in the end because we have a lot to cover. So the example I've showed you is very interesting, I think, because it can suggest some potential problems. So you can see here the class wrapper, and you can see that it takes some kind of type. Now, it might have been the case that the type that it accepts is also somehow affecting the evaluation of the function. So I wanna show you here a solution that is not part of the language yet, and this is a proposal by Isabel Murta, and it's offering basically to add those concepts to the language, and the way to use those is to break the recursiveness of trying to evaluate a concept on a type that is accepted from outside on a class that's again been evaluated with the concept. So this is something I actually stumbled across while working on in a work group related to executors. But I'm sure there's a lot of examples online, but this is probably not something that you will stumble across every day. But in case you are defining a complex library, you might want to keep in mind these in order to identify that you're accepting a type that already been evaluated with the concept that you're evaluating inside the function. So this is very important in case you get a compiler error. And okay, so this is the last part of my talk. And now we're going to see advanced method for compile time logic. So as I said, C++20 gives us a lot of different tools. And I want to start with things related to lazy evaluation. So, and when you write template code, metaprogramming code, you could just address that as moving code to compile time, which is, of course, something that is done, that you're doing by moving to templates. But you could also address it as moving your logic to compile time. And that means you could perform more tasks in compile time, considering conditions. So, as I said, lazy evaluation is an interesting thing that you can do for the more advanced template metaprogramming scenarios. So the benefits of lazy evaluations would be to avoid creating temporaries that are unnecessarily and costly. And we could also improve our compile time of the program. I'll show you later in a way, but with a bit of a different method. So expression templates are an old method to do that, and it exists for quite a while. And I'm going to go over this and show you that we could actually implement that and try to address that as a more general. Try to avoid addressing the specific example that is a very popular one, and see the general design guidelines that are here for creating a proxy object to hold your logic in order to avoid the instantiation of temps. So okay, so let's start. So here we have a wrapper for a vector, which is again the most common example for expression templates, since creating a vector is costly. And we can have a constructor, it takes size, and again a constructor that a copy constructor that takes another vec wrapper. And we have the implementation of the equal operator and the plus. And I haven't added this in this slide, but of course we have the two implementations for operator reference and clause. And here you can actually see the usage of this wrapper function. So we could eliminate this plus operator from our original class and add a free function that overrides, doesn't override because we eliminated, but it implements the operator plus. And here, if you can, as you can see, we're not accepting we're not producing our vec wrapper. Instead, we're producing a new type that's called sum. And this new type, this new struct, as you're gonna see in the following slide, is gonna hold our vectors that we were trying to perform operator plus on. So here is our sum class. So you can see here the class, it gets type of, this is the type that is part of the, this is the type that the vector holds. It's not necessarily to get it, that's why it's gray, but you might want to do something with it, so it's an optional. And here you see two different types that represents the two vectors that you receive in order to evaluate. And this class constructor is basically saving the types that you got for the vectors in a reference to them inside the struct. So this is very simple. As you can see, this is a very simple form to do. I think it's very readable to do something that is very complex. So here you can see the implementation of the operator clause, and this implementation is what creates our lazy evaluation. So as you can see here, we're returning the sum of the objects. So as I mentioned before, expression templates are very common, and again, you can watch a talk by Klaus Egenberg from CPP Now 14. He was talking about Blaze library that he implemented, and giving very good examples there. So I really welcome you all to go and watch that. But again, we've created sort of a lazy evaluation, and this is what we were aiming for. And here you can see that the temp is not being created between every time we're calling the operator plus, we're saving the different vectors in our sum class. And then we basically only evaluate this in the final evaluation and the injection that actually instantiates the Z. So it's not this one, actually. All right. So ranges are optional way that there could have been a way to solve this lazy evaluation thing and implement something that is very similar to what we just saw in a much simpler way. But they're not just yet, because ranges were added to CP+20, but left out was the zip and zip width view ranges options. And you can experiment. Ranges are basically imported from Eric Nibler's ranges version 3 library that is part of Boost, and you can experiment with them. But basically, this is how it could have looked like in case we would have got zip and zip width in the standard. So this is the plus operator, and you can see the classic definition that you would have expected. It implements the operator parameters, and it returns the plus of the two types that it got. And here we can see the usage of the zip with view operator. And by the way, in the standard would have been suggested as zip with view. Here it's under the namespace view. And the fact that this is in red is to emphasize that this is not part of the standard. This is because in the standard they're called views. So again, you can experiment with that in the snippets that I'll post later in my GitHub if you're interested. And I think this is very elegant and very simple way to create lazy evaluation. I would hope that in the future we'll also get those. So the problem with them was reference, the return types reference issues. So we're probably going to see them in the future. Sorry, one more thing that I forgot to mention. If you're interested more in understanding ranges, there's also a talk from last year's CppCon by Dvir Itzhaki, which is also a member of my national body, and you're most welcome to watch it. I think it's a very funny one, a good one to explain ranges. So as I said before, and I think, I mean, to my opinion, it's a very interesting finding. The constraints evaluation have 4 stages. So I've mentioned them before, the by order. And I took here, evaluation 4, which is the last evaluation syntax, and evaluation 1, which is the first evaluation syntax, meaning putting the concept here at the restricting the type the template accepts. Sorry, and putting the concepts as requires at the end of the function. And I would have expected the performance would be equal, but in fact, what I found was that using the evaluation first form would actually create better performance. So this is the stack that I've been using. I've been using GCC Trank and flag clearly of 6+2a, stdlib libs+, and this is on x86 and with optimization level 3. Now, I would encourage you to try and test that on your machines and to see whether moving the condition to this place, which is evaluated first, will create some performance optimization. Here, I'm sorry I haven't mentioned it. I'm referring specifically to the time that it takes the compiler to create the program, not the runtime of the program. And of course, it could have been implementation detail, but one thing I do think that is worth understanding from this example and in general for designing a code with concepts is that I would suggest you to put your breaking conditions here in the evaluate 1 form. Of course, you could put the add ones here as well by adding conjunction, disjunction, etc. But I would suggest to do something like putting the breaking conditions in here and then have the additional conditions here. And in order to improve performance, the compile time of your program. So what we will do is that if the condition, especially if your spectrum of suitable types is very limited, it will break the condition very early in the compilation process. Therefore, I would expect it will optimize your compilation time. So I think that's very cool to discover additional capabilities that we have by using this additional syntax that's accepted in C++20. So takeaways from my talk. So first of all, I would say that I think we all agree now that template metaprogramming is a very powerful tool. C++20 extends the vocabulary for using this tool, and I would even suggest that it create a simpler and clearer way to for the developer to express what he wants to be limited, and a stronger way to use compile time for logics. In addition, as I said, the readability of the code is increased, and I would also expect that a few of the improvements that I mentioned before would be part of the standard in the following years. So I think you should stay tuned and be able to add them to your code bases whenever possible. And in addition, I think that's, I mean, I would hope that everyone's gonna move to C++20 as soon as possible, because I really think those tools are giving us additional flexibility regarding our code. And even if you're not a library developer, knowing those evaluation, knowing the order of evaluation that I've mentioned before, and understanding overload resolution and ADL are powerful tools even for code that doesn't need extensive use of template metaprogramming. And I would hope that by this talk, you're more familiar with them, and you'll go and search more about those later on. And let's strive for more extensive use of templates. So books that you can go over, and those are clearly classics. You could read those. The C++20 template complete guide is aligned to C++17. The one in the middle is actually was published not very long ago, and is more advanced. But I think this one's clearly more covers broader material. And of course, you could go to the classic book publication. And of course, there's much more books on the internet. I would love to get your recommendations as well. I think this topic is fascinating. So a few links that I've mentioned during the things that I mentioned during the talk. So CppCon talks, those are all happening now or in this session, C++20. So as I said, there's template metaprogramming with emphasis on type traits by Judy Hanks, and Back to Basic Templates by Andres Ferti. And I apologize if I don't pronounce correctly all the names. I think it's also a very good talk to get you started, and it also explains about much more about variadic templates. And another thing that I think that is tomorrow, I think perhaps later or tomorrow, there's a very interesting talk by Timur that will talk about all new features for C++20. And also, I'm sure it will be a great talk. I haven't had a chance to see it yet, by Ben Dean, that also talks about generic algorithms. So the previous year's talks, first one is by John Clabb for more the template techniques, and everything things that you saw regarding enable if, he explains much broader, and I haven't got deeper into that because I was focused on C++20. But if you want the background, if you're unable to use C++20, which is also common, you're most welcome to go and look deeper into his talk and understand the implementation for previous versions of C++. And and I also mentioned Yitzhaki's talk for ranges, which is fascinating to my opinion. And Klaus's talk from 2014 is explaining very broadly about how he used expression templates for Blaze. Technical data that I mentioned, I'm not going to go over all of those, but the papers that I've mentioned are also here. And there's, of course, link to CPP Insight by Andres Fertig that actually unpack your templates and present them, I think, in a very readable way. So I would really recommend going that. And again, the papers that I've mentioned appear here. So thank you very much. I will stay at the tables and take questions there because, as you can see, I got very close to the end of my time slot. But I hope you're now inspired to go and explore more of C++20 templates. And again, if you want to play with the code, with the snippets, I will post all of those, all the lists in my GitHub. So you're most welcome to go there and experiment with them. And you can always feel free to email me. And I think that I would love to hear from you if this talk have affected you and made you insert more templates to your code base in whatever version that you're using. So thank you very much.